So, now let us start looking at the applications of op amps in circuits with memory, right. And the first circuit, what memory, what elements, circuit elements do you know which have memory? The capacitor and the inductor, right. With a lot of circuits, unless you're dealing with power applications, it turns out that inductors have become, for signal processing purposes, inductors, at least at a whole lot of low frequencies, basically the kind of inductance you need becomes so large that it is not feasible to have inductors. For most part, as far as signal processing is concerned, at low frequencies, capacitors are basically the dominantly used memory elements. So, the first operation that we can think of with memory is integration, right. So, and the idea basically comes from this. So, we say that right, this is R1 and R2. So, what is if the op amp is operating in negative feedback, this voltage is 0. So, what is happening to what is happening through R1? A current of Vi by R1 is flowing through R1, and then that same current flows through whatever is there in the feedback branch. So, that current is basically causing a voltage drop of Vi times R2 by R1. All right. Now, we want to build an op amp based circuit which takes a voltage and puts out a voltage which is the integral of the input voltage, right. So, but what is the only, what is the element that which integrates something and gives you a result? A capacitor. So, this is let us say this is I of t and this is V of t, right. What is V of t? Is nothing but 1 over C integral I of t dt. So, the capacitance integrates a current and generates a voltage which is proportional to the integral of the current, correct. And so, that is the what do you call that is the Lego block we have, which is capable of integration. But we want to integrate a voltage and generate a voltage. So, staring at the left hand side, is there something that you can think of that will do the job? Replace? Replace R2 with capacitor. Why? Yeah. So, basically this R1 is taking Vi and then thanks to negative feedback, assuming negative feedback still works, the negative node of the op amp, the inverting terminal of the op amp is going to be at virtual ground. So, Vi is basically converting, is being converted into a current through R1, right, and that current is flowing through the feedback branch. So, if we replace R2 with an integer with a capacitor, so let us call this R. So, this is Vi by R, this is R, and this is C. So, this current Vi by R flows through C, and what is the voltage across the capacitor? V by So, 1 by R C integral V I of t dt. So, the output voltage will be minus 1 by R C integral V I of t, right. In the Laplace domain, V O of S by V I of S is nothing but minus 1 over S C R. Okay. And if you draw a Bode plot for the integrator, the Bode plot basically is log omega, and this is log magnitude of 20 log VO by VI. How will this look like? It will fall off at minus 20 dB per decay. And what is the unity gain frequency? 1 by RC radians per second. All right. So, this is called the unity gain frequency of the integrator. Now, why is it called unity gain frequency? So, mod VO of j omega by mod VI of j omega is 1 over omega RC, and at omega equal to 1 over RC, mod of VO by VI becomes equal to 1. Okay. So, what is the angle of VO by VI? The transfer function has got a magnitude and an angle and or phase. So, what is the phase of the transfer function? Yeah, minus pi by 2 radian, right? Right. So, it's got a j in the denominator. All right. Now, it is also very common, a very common arithmetic operation to add it's straightforward now to do weighted integration. So, you would, let us say the task is I want to add multiple voltages, right, and integrate their sum. What will we do? Okay, if you want to, so let us again go back to the basics. So, if you this is an inverting amplifier. Let us say the feedback resistance is R, and this is VO, this is VI. Let us say we want VO by VI is minus K1, or let us say this is V1. We want minus K1 times, VO by V1 is minus K1. What should we do? The resistance value should be R by K1, right. Now, let us say we want VO by VI. So, in other words, VO is basically minus K1 times V1. Okay. So, now let us say we want VO to be minus K1 times V1 minus K2 times V2. What should we do? We will add another resistor of value R by Okay. Alright, so if you have n voltages, then you can all add them up. I mean, how is addition being done? Well, this voltage is being converted into a current. This voltage is also being converted into a current. The currents are add up at the virtual ground and go into the feedback element and generate a voltage across the feedback element, which is simply the proportional to the weighted sum of the Does that make sense? Okay. Now, if you want weighted integration, what should we do? Yeah, well, we know that the capacitor integrates current and generates voltage. So, that is straightforward too. Put a capacitor there. So, what is the output voltage? Minus K1 by RC integral of V1 of t dt minus K2 by RC integral V2 of t dt. Okay. Or VO of S is nothing but minus K1 by SCR times V1 minus K2 by SCR times V2. Okay. So, one thing I would like to draw your attention to when you are trying to realize an open loop integrator, right. So, it turns out that let us assume that the op amp has got some tiny offset, right. What is offset? Basically, there is equivalently there is some, let me not mess up this part, let me copy and paste it. Okay, so let us assume that there is some offset. Every op amp will have offset. All right, and let us say you are trying to operate an integrator open loop, correct. So, what will this voltage be, assuming that there is negative feedback? What will happen to this voltage? No, this is V off, and let us assume that Vi is 0. All right. So, what is this current? This is V offset by R. So, what will happen to that voltage? One by RC integral V offset, integral of V offset, right. So, V offset is a DC. So, this is going to be integral V offset. So, what will happen? What comment can you make about the output voltage? Let us say we turn on the circuit, the capacitor is initially uncharged. So, what will happen? What will be the output voltage? It will start at 0, it will start at V offset, because the virtual ground voltage is at V offset, and then it will keep going up and up and up, right. Eventually, what will happen? The op amp will saturate. If V offset is positive, if V offset is negative, it will saturate to the negative state. Okay. So, now if so what is the moral of the story? Yeah, so if you try to operate an integrator in open loop like this, right, without DC feedback, I mean, so basically if you remove the capacitor, I mean capacitors are doing nothing for DC. So, if you remove the capacitor, what comment can you make about the op amp? It's in open loop, and remember that all capacitors for DC can be removed, correct. So, basically if there must be DC negative feedback around the op amp for it to have high gain. And which is equivalent to virtual ground, virtual short being applicable and so on. Right. So, if you go into a lab and try to build an integrator like this and expect that I will put in a waveform and the output should be the integral of the input waveform, you will be in for a surprise, because the output will either be plus VD plus VDD or minus VDD. If the output is plus or minus VDD, what comment can you make about this virtual short? Can we say that the difference between, I mean, the two input terminals of the op amp can be behave like a virtual short? No, because that only applies when the op amp has an infinite DC gain or very large DC gain, right. But because the op amp is saturated, its DC gain, I mean, you change the input and then the output doesn't change at all. So, the gain is actually 0. So, therefore, this virtual short concept doesn't work, doesn't apply at all, because the op amp is saturated. I mean, if there was no saturation for the op amp, if the output could go to infinity and the op amp wouldn't get saturated, then we can still operate it in open loop and the output will go to infinity, right. But of course, in reality that's not possible, and therefore you can never operate an op amp without DC negative feedback, right, okay, and expect it to behave like a virtual short. Is that clear? All right. So, that's a good, I mean, that's something that you should always bear in mind. So, turning this observation upside down, if you go and let's say you have a circuit and you find that the two input terminals of the op amp are at the same potential, correct, and then what can you conclude? There must be a DC negative feedback path around the op amp, otherwise the two input terminals can never be the same, right. I mean, of course, in a practical op amp there will be some offset. So, if you go and measure the two input terminals, the difference will be that offset, right, okay, because what you are going to be measuring, it's not as if this it is not that this offset is some battery that is stuck on at the output. So, basically this is, if you I mean that battery is the internal to the op amp equivalently. So, you only have access to this terminal and this terminal, and if the op amp is a negative feedback, then if you measure the potential difference between the two terminals, you will measure plus or minus V offset depending on which is the positive terminal of your multimeter and which is the negative. Is that clear?